Okay, yeah. So in fact, now that we have completed some quite a significant portion with respect to differentiation, we will devote some time to discussion of doubts and questions from the assignments. Okay. So yeah. So I think Nishay, your doubt is in the third assignment, right? The one I gave last time.
Yes, sir.
Okay.
Yes.
Any doubts pending before that in assignment 1 and 2? Anybody has any doubt pending or any question you want to discuss?
Sir, from assignment 2 also, that last question. The
Assignment 2,
2
the last question. No? Okay, just give me a
Yes,
moment.
sir.
Okay, so let's start with that. Okay. So today we'll start with some doubts and discussions from the assignments. So assignment 1, I'm guessing nobody has a doubt, I hope, right? If there's anything, please let me know. Okay, so let's start with the worksheet 2, last question. Just give me a moment, I will bring that up on the screen. Yeah, sorry, I forgot who had the doubt in this question. Question 5 of assignment 2. Nischay, it was you. Okay. Yeah. So the question is clear. What it's saying basically.
Yes, sir.
So see, like obviously, if you have learned a bit of calculus before, you can understand that we can do this question by integration also. But here I will not be doing by integration. Here I'll be discussing from what we know already, which is differentiation so far. So it's saying that y is a polynomial function of x. Okay. So sorry, this should not be y, this should be of x. Okay. So it's a polynomial function of x. So that generally means that what type of function y is, it is like this: some constant plus some constant into x plus some constant into x square plus, so it's a power series like this. Let's say going up to x to the power n. But now immediately it tells me that dy by dx. Now dy by dx or rate of change of y, this is which type of function? Is quadratic. Okay. So from my experience of polynomials, I know that when I differentiate a polynomial, the derivative I get that has one less power. Okay. Or the degree of that polynomial that I get on differentiating will be n minus 1 if this one is n. So this will become a1 plus a2, sorry, plus 2a2x. Okay. Plus the next term would have been a3x cubed. So 3a3x square, like this, going up to the last term, which will be n into a to the an into x to the power n minus 1. So this is the general thing. If I say that y is a polynomial, then differentiation of this should be like this. But now this one is a quadratic. So that means this is going up to only power. So n minus 1 is only 2. That means what is the maximum power of the original polynomial, or what's the degree of the original polynomial? It's only 3. Is this point clear, Nisha?
Yes, sir.
Okay, so now I can simplify the question. So this is just to demonstrate, but actually you can just understand this directly, that okay, if the derivative is just quadratic, that means the function should be cubic. इसका maximum power कितना होना चाहिए? 3 होना चाहिए. So let's assume. So let us assume that what is happening, that y is some, let's say, some coefficient of x cube, which is p I have taken. You can take any symbol, it doesn't matter. Just for reference, I have taken this, plus r into x plus s. So what are my unknown quantities? P, Q, R, and S. Okay. So now I can see that differentiation of this would have given me 3px square plus 2qx plus r. So first of all, when I compare this derivative with the given derivative, when I compare these two, so what I can say that, okay, a is equal to 3p, b is equal to 2q, and c is whatever r would have been. Okay. So I need to solve for all this to get these answers. Now I have 4 unknowns here. P is unknown, Q is unknown, R is unknown, and S is unknown. Once I know P, Q, R, S, I can calculate the value of A, B, C, polynomial, everything, right? So clear so far?
Yes, sir.
Okay.
Sir, we
Now,
can do
how?
this by integration as well.
Of course, Ibrahim. We can do this by integration, but that's what I said, that if we haven't learned integration till now, let's see we can make use of what we have learned. So we have learned this simple thing that, okay, if we differentiate some n degree polynomial, we get n minus 1 degree polynomial. So that means if the differentiation of y is giving me quadratic function, that means y must have been a cubic function. So I can just start with this assumption and try and apply algebra here. So you can go with that method also, right?
Yes, sir.
Okay. So now see, I need 4 conditions now to find 4 unknowns. So 4 conditions are given to me. This is one condition, this second condition, this third, this is fourth. So we have to just substitute in each one. So the first 3 are given as relations between y and x. So in which equation I'll substitute? I'll substitute in this first equation. So these 3 I will substitute in equation 1. So what I'll get that, for example, the first one will give me y is 0 when x is equal to 0. So 0 is equal to s. That's what I'm getting from the first one. Then the second one is giving me that y is 6 when x is equal to 1. So that means p plus q plus r. S already is 0. That should be 6. So that's my second term. Okay. Third term is telling me that again y is 0, but when x is equal to minus 1. So when x is minus 1, you can see this is minus p plus q minus r. So I'm getting these 3. And finally, this one I should substitute where? I should substitute in this equation, the second equation. So I'll substitute this condition in the second equation. So that is going to give me that dy by dx, that is 2 when x is equal to how much? 0. So right hand side is r. So now that's it. Now you can see that these 4 things, if I solve this one, this one, this one, and this one, I'll get each of the terms p, q, r, s, and from that I'll get each of the terms a, b, and c.
Yes.
Understood, Nisha? So it's a way of working backwards. Okay. Because I'm given dy by dx has degree 2, so I'll assume that y has degree 3, and the unknown quantities are the coefficients of x square, x cube, x, and the constant term, all this. So how I'll find these? By using the conditions which I've been going backwards. And of course, we can do this by using another thing called integration, indefinite integration, which we'll be learning in, let's say, a couple of classes more. So at that point of time, we can come back to this question and solve it by another method also, right?
Okay, sir.
Okay. Anything else in worksheet 2? Anybody has a doubt? Okay. You might have noticed that in the hints and solutions I had given, this one's answer, unfortunately, I had written wrong. Okay. I had missed out this 2. But I think I discussed it in the last lecture. So just, correct the answer key from my class notes of lecture 3, right? Any other doubt or any other answer you feel we need to discuss? Something?
Yes, sir, I have a doubt.
Yeah, tell me, beta.
Sir, in the question we just solved, sir, we get P, Q, R and everything, sir, as 3, 1, right? So after that, sir, there is one more step, no? So because y is equal to ax square plus bx plus c. So it's
No,
not
that's not y, beta. Y is px cube. See, that's dy by dx. Okay. So we have to express y as a function of x, no? Understood the point, no? मुझे ये करना है ना, y as a function of x.
Y becomes
हाँ, तो p का वैल्यू कितना आया था?
x square plus 2x, no?
Correct. Okay.
So but then we have to differentiate it. So to get ABC.
No. So a तो पहले आ गया था ना. A I knew was 3p, ना? So p had come out to be how much? 1. Okay. Q, if I remember, had come out to be 3, maybe. Correct?
Achha, sir, I got inverted values. I got p is equal to 3, q is equal to 1. So sir, my A is 9, B is 2, C is 2.
Okay, let's just recall what equations we had. We had y is equal to px cube plus qx square, okay, plus rx plus s. And while solving, what we had got was that s was 0, correct? Then we had got p plus q plus r was 6, correct? That was one of the equations. And minus p plus q minus r was 0. That was one equation. Okay.
Yes, sir.
And what else we had got? We had got r was 0. Sorry, r was 2. Okay. So solving all this, let's see what we got. So from these 2 equations, if you just add them, you get 2q is 6, so you get q is 3. Okay. And once you put q as 3 and r as 2, so what we are getting p as? We are getting p as 1. So these are the solutions we are getting for p, q, r, and s. Okay.
So I think I made a calculation error.
Okay. So understood, no? So y is coming as what? X cube plus 3x square plus x, that's
2x.
it. S is 0. Sorry, plus 2. Because
yes, sir, I got the same thing.
Plus 2x. Yeah,
first A and B are inverted. Okay, sir.
Okay, now isko differentiate kar lo chaho to, so then differentiate or just compare with these equations that A is 3p like that. So if you differentiate, you can see this is 3x square plus 6x plus 2. You can also see that A's value is therefore how much? 3, B's value is how much? 6, and C's value is also 2. Okay, so everything lies in the algebra only. The thing is that, you know, we have to just be patient in solving these kind of things, because, you know, there are a lot of steps, you know, a lot of scope for making mistakes. So just remember a couple of things that I keep telling you people, that, you know, don't be in a hurry initially. Write down all, especially, you know, in things like chain rule. This though was still okay, but now when we look at the next assignment, like chain rule, people have a habit of using that formula directly. That differentiation is f prime of gx into g prime x. But that formula you should directly use only when you have done a lot of practice. Initially, what you should do, you should go with the 3-step method which I've given you. That is, first step, substitute the dummy variable. So express y as a function of z or u or any other variable. Then calculate by the chain rule. Then substitute, then re-substitute. So it might seem that it's a much longer method, but actually that method will ensure that you're not in the habit of making any type of mistakes while solving. And with practice, you'll see you'll be able to do the steps directly. You'll be able to skip some steps. Okay. Anyhow, so anything else in this second assignment or second worksheet?
Yes, sir.
No, sir.
Question 2.
Tell me, Beta, which one?
Sir, question 2.
Question 2. Okay. So tell me which part of question 2 you're having the difficulty with?
So like I didn't understand the question basically. So if you help me out with that, I'll try
See,
it on my own.
What is the question telling us? That it's just imagine this like a drag race. Okay, so two cars are starting from the same initial point or the same x coordinate. Let's say we are taking this as our x-axis. Okay, but they are moving along parallel tracks, and if you see, their displacements are given as a function of time. So at some general time t, if we assume that the object A is somewhere here and the object B is somewhere here, of course we'll say that, see that after some time B would have overtaken A. So this will not always be the case like this. So this is nothing but the displacement or distance, whatever you say, because it's a straight line motion. So distance and displacement are same. Okay, so these are given to me as functions of time. So SA as a function of time is 8t square and SB as a function of time is 4t cube. Okay, so what other information this is telling me? Now I know from kinematics that what is instantaneous velocity? It is instantaneous rate of change with respect to time of distance, correct?
Yes, sir.
Yes, sir.
Understood this point? So VA कितना आ जाएगा? 8t square को differentiate करना है मुझे with respect to time. So it is differentiation of this or instantaneous rate of change of this. So it is differentiation of 8t square with respect to time. So for this, I'll just use this principle. 8 comes outside and differentiation of t square is 2t. So VA, that is the instantaneous speed of the object A, is 16t as a function of time. So this is clear how we got this now? Now similarly, how we'll get VB? From this we can see that instantaneous speed of B is rate of change of displacement of B with respect to time, or distance of B, whichever we take. So it is differentiation of this term now, 4t cube. So likewise, differentiation of this term, you take the 4 outside and differentiate t cube. So you have 3t square. So instantaneous speed or velocity, whichever we take, is 12t square for B. So now we have two informations. Now, we were already given the distances or the displacements. Now from this, we are also generating the information that instantaneous velocity of this guy is 12t square. Sorry, this guy's velocity is 16t, and instantaneous velocity of this guy or speed of this guy is 12t square as functions of time. Okay, so far you're clear now?
Yes, sir.
Okay, now see, everything that you need to answer in the question will come from substitution here. For example, the first part is just direct substitution. That at 1 second, you have to find out is A ahead of B or A is behind B. So for that, if something is ahead, its distance will be more. If something is behind, its distance will be less. So just substitute t equal to 1 second. So at 1 second, you will see A's distance is how much? 8. Whereas B's distance is how much? 4. So that means A is ahead. So it's ahead, it's not behind. Got it now?
Yes, sir.
Now you want to answer whether A is moving faster or B is moving faster. So how we'll know that? From the speed. So again, at t equal to 1 second, you can see what is A's speed. A's speed is, you'll get by substituting t as 1 over here. So it is 16 in meters per second. These are in meters. Okay. What about B's speed? It is 12 meters per second. So which one is moving faster? A is moving faster at that
Sir,
instant.
I have a doubt in the
Yes.
first part. Sir, in the first part, we can also substitute VA is equal to 16 and then multiply it into 1, but we will not get the same answer.
No,
Why
no,
is
no,
it
no.
so?
How we can do that, beta? VA is 16t na, as a function of time. Is V constant over here? Nahi,
No.
na? So for example, at 0.2 seconds, at 0.2 seconds, what is the speed of A? It is only 3.2 meters per second. Okay, at 0.4 seconds, it is 6.4 meters per second. ठीक है? तो मैं नहीं बोल सकता हूँ ना कि speed into time नहीं होगा ना distance.
हाँ, yes sir, समझा.
Got the point?
Yes
In
sir,
fact,
कोई
अगर आप
linear
ध्यान से
function
देखो
नहीं है,
ना,
इसीलिए ना.
हाँ, linear function नहीं है, but at the same time अगर आप ध्यान से देखो यहाँ पे you can apply one more thing, that this is what type of function? It is a quadratic function, so you can relate it with uniform expression. So in fact, what this is telling me that as far as A's motion is concerned, A's initial velocity would have been 0, right? And A's acceleration would have been how much? Constant and equal to how much? 16 meters per second square. So then you're getting this as ut plus half at square. What's the point now?
Yes.
So then you can also relate this instantaneous speed by the formula method, that v is equal to u plus at. So va should be equal to initial velocity of a plus acceleration into time. So you can see that speed of a as a function of time will automatically become 16t. But that method now you cannot apply to the second one, because it's what type of function? Cubic function. So for cubic function, you cannot apply these velocities. I mean, these formulae, that v equal to u plus at, because it has a non-uniform acceleration. So further, if you observe in terms of kinematics, there's another story that these two equations are telling you. And that story is that A is having uniform acceleration, B is having non-uniform acceleration, because B's displacement is a cubic function of time. Understood the point now?
Yes.
So when we have to judge their displacements at a given instant, we have to substitute time directly in SA and SP. When we have to judge their instantaneous velocities at a given instant, we have to substitute the value of time at that instant in VA and VB. And that is how we'll answer each of these questions. So understood A and B partner?
Yes sir.
Okay. Now C ke liye kya hai? C, now see, you have to understand why the question is making sense. Okay. First of all, it is asking at what point of time B overtakes A. So see, A and B started from the same point. Na? So if B is overtaking A, it only makes sense if A initially goes ahead and then B catches up and overtakes. Got it, na?
Yes sir.
Agar B pehle se hi aage hota, then it would not make sense only na, that when B overtakes A. So, and that evidence you're getting in the first part, for example, you can see in the first part that is why the questions are coming in this order. Actually, you can see in the first part that A is actually ahead of B. But if you put a little bit of thought into this now, you'll see this is a cubic function and this is a quadratic function. So eventually the cubic function will dominate. Na? It will rise at a more rapid rate because it's t to the power 3.
Yes.
Are you understanding my point, people?
Yes sir.
Yes, sir.
So, for example, you can see that at a very later time, like 100 seconds, B's displacement will have an order of magnitude of 10 to the 100 to the power 3. So that will be 10 raised power 6. Whereas A's displacement will only have an order of magnitude of 10 raised power 4. So B is so much ahead. You know, it's literally like infinitely ahead compared to A. So eventually we know that B is going to be ahead. But also by calculating the first part, we got an idea that initially A was ahead of B. So that means in between at some point of time greater than 1 second, at some point of time after 1 second, B has overtaken A. So now we want to calculate exactly when B would have overtaken A. Okay, so let's say this was 1 second. At 1 second, A was ahead and B was behind. We know that. But there must be some time which we don't know about when this is happening. A and B are coming alongside, so that now at a time greater than that, somewhere over here, A is behind and B has gone forward. So by now the overtake is complete, but this is the time when the overtake is happening. So at the moment when the overtake is happening, what is happening? B's displacement should just become equal to A's, because after the overtake, B's displacement is becoming greater than A's. Okay, so the condition for the overtake is that eventually B's displacement should become greater than equal to A's. And exactly at the moment when they are equal, that is when the overtake is happening. And that is the middle diagram over here. This point is clear, no?
Yes.
Okay, so uske liye kya karna hai? We have to just substitute this. Okay, so SB should be greater than equal to SA, or at the moment when it becomes equal to, that is when the overtake is happening. So basically 4t cube should be greater than equal to 8t square. We solve for this and we had seen that we get the time as 2 seconds. No? So basically we'll get time as greater than equal to 2 seconds. So 2 seconds onwards, B's displacement becomes more than A's. That means exactly at 2 seconds, that is when B is in the process of overtaking A. Before 2 seconds, B was behind, and after 2 seconds, B is going forward. Okay, na? So is this clear? The visualization of this problem is also clear?
Yes, sir.
Yes, sir. Sir, one more thing, that when we calculated instantaneous velocity, then like if we substitute some value of t and then multiply it by time again, then we'll get the distance travel in that instant, right?
No. See, that is the thing you have to understand. See, what is happening now? Your distance versus time graph. If you visualize your distance versus time graph, that's a non-linear graph, no? So if this is your distance versus time graph, in this type of situation, because it's a non-uniform velocity, it's curved like this. So at some particular instant of time, what is the velocity? It is the slope of the tangent, no? So ये वाला जो slope है, वो आपका velocity है at this instant. So if you multiply the velocity with time, what you will get? You would have got the distance as this much, no, from here to here. But actually you can see the distance is not this much. The distance has increased at this time to somewhere here, because the distance is actually following which graph? The red colored graph. The blue one is only the tangent at that point. Are you following my point, beta?
Yes, sir.
Okay. So for example, okay, if I say what is the distance traveled in a very short interval of time, like a microsecond over here, then I can say, okay, for that microsecond, the actual curve and the tangent are almost the same. So I can say that delta S is equal to V into delta T. But basically that will be like saying that ds is equal to V into dt. So this equation is correct. But delta S is not equal to V into delta T, because delta T is a large interval of time. dt is a short interval of time. It's clear now?
Yes, sir.
Okay. So that is where the whole thing of integration will come in next. But here we don't need integration, because we already know distance as a function of time. Na? So for example, if I ask you, yeah, Nishya, I'll come to you. If I ask you what is the distance traveled by A from t equal to, let's say, 2 seconds to t equal to, let's say, 4 seconds. So all you have to do is calculate the total distance at 2 seconds, total distance at 4 seconds, and subtract the two. So that distance traveled will be equal to 8 into 4 square minus 8 into 2 square. That's it. That will become your answer. You don't need to do any integration or anything, right? Yeah, Nishchay, what is your question, beta?
Sir, so in general, we can only say delta S is equal to V into delta T when it is a uniform velocity, right?
Only when it is a uniform motion. Yes, correct. And in that also there's a lot of technicality. We can say distance is equal to speed into time when speed is constant. But we can say displacement is equal to velocity into time only when velocity is constant. Now speed is constant doesn't mean that velocity is constant. You're getting my point now? It could happen that an object is moving along a curved path like this, but with a constant speed. So the distance will be changing uniformly with respect to time, but will the displacement be changing uniformly with time? No, because it's going in a curved path. On the other hand, an object could move in a straight line path with a uniform speed. In that case, the velocity is also constant. So the distance is velocity into time.
Yes, sir.
Okay. And all these technicalities we'll understand when we come to the chapter of kinematics. So by then you would have done vectors also, and on this part we would have done calculus also fully. So you will understand these things even better at that stage, no?
Okay.
Okay, now what about the fourth part? It is clear. In that we have to just find at which point of time B's speed becomes more than A. So if B is actually overtaking A at 2 seconds, you'll realize that the speed of B had to become more than A before only, because B had to catch up with A. Na? Initially A moves ahead of B. That means initially A's speed is more than B's. Okay, but eventually B catches up with A. So that means B has to pick up more speed before it catches up. So we expect that the answer should be less than 2 seconds, and that is what you get, because the condition for B speed to become more than A speed, that condition is what? That VA should be, VB should become greater than VA. The instantaneous speed of B is greater than in the instantaneous speed of A. That is the moment when the speed becomes more than. So what was the instantaneous speed of B? It was 12t square. This should become greater than this one, 16t. So we had seen that this time was greater than 4/3 seconds. So which is 1.33 seconds. So you can see that, B is picking up more speed than A between 1 and 2 seconds. And that is why by the time you're coming to 2 seconds, B is actually overtaking. Okay, so I hope the whole thing is clear for you people now.
Yes, sir.
Yes.
Yes,
Yes,
sir.
sir.
Yeah, so this was just to give you an example of how we use calculus and the concept of rate of change in actual physics problem involving some motion. Okay, of course we'll see lots of questions like this in kinematics. Okay, where also those complications will come in, that when it's straight line motion, when it's not straight line motion, the difference between distance and displacement, velocity and speed, etc. All these things will also come in. Okay, anything else in worksheet 2?
No, sir.
Okay, good. Let's switch over to worksheet 3 then. Just a moment. Yeah, so any doubts in worksheet 3 from the first question, any part? The instantaneous slope of tangent.
Sir, I did not get that E part in first
Oh.
go.
In question 1, no? Okay, so I'll come to that. Anybody has a doubt in part 1 to D? Okay, question 1E. Okay, so let me just, so the question is y is equal to e raised power sine x, and we have to find the derivative at the point x equal to 0. So for the function y is equal to e raised power sine x, we have to find the value of the derivative at the point x equal to 0. Okay, so that means we have to find the value of dy by dx. So first step is we have to find dy by dx is how much, and then we have to find the value of dy by dx specifically at the point x equal to 0. So now looking at this function y is equal to e raised power sine x, we can see it is a composite function. Okay, so this is the key thing in these type of questions. We have to learn to recognize a composite function. So typically you can recognize it because there are two operations involved, one on top of the other. On x we have operated sine, and then we have raised that sine x as a power of e. So that means you've done two operations. But if you're having confusion whether this is a composite function or not, the way to understand its composite is just to think of how you get from x to y, how you reach from x to y. So first you must have operated sine on x, so you got sine x. Okay, so the first function you operated is sine, and then on that you operated the function e raised power. So you got y is what? E raised power of sine x. So you can see it's a composite operation. You know, your g was sine, so this is your gx, and your f was e raised power, so your y is equal to e raised power of gx or f of gx. So it is a composite function. So how we'll do the differentiation of composite function? We have to do it by chain rule. Okay, now for those of you who practiced for the composite function enough, you can see that if you just express this as f of gx, then you can understand that differentiation is f prime of gx into g prime x. Now here, what is f? F is the exponential function. So what is f prime? It is exponential. So it is exponential of gx. And what is g? It is sine. So what is differentiation of sine? It is cos. So it is cos x. So you can do it directly like this. But at this point of time, I don't recommend you to do the question this way. I recommend you to do the question in the lengthier method, which is the substitution step method, which I have taught you in the last lecture. Okay, so this is the shortcut way of doing the question, which you should do after doing lots of practice. For example, after completing my worksheet and doing the questions, at least the ones which I have given you for homework last time from the module. After you complete all this practice, then you will be in a position where you can do these steps immediately, okay, without making any mistake every time for every question. Otherwise, if you start, doing this kind of shortcut work right from the beginning, you're likely to make mistakes in at least 1 out of 5 questions, okay, which is avoidable. So instead of doing this, instead of this shortcut method or the direct application of chain rule, which is this, what we'll do is we will apply the step-by-step method of chain rule. So step-by-step method of chain rule, how it works. So we are given the function y is equal to e raised power sine x. So understanding that this is a composite function. Now step 1, we apply the substitution. So our dummy variable is equal to sine x. Okay, that is our assumption. Okay, so y becomes very simple. Y becomes e raised power z. Then our step 2, that is the application of chain rule. So the statement of chain rule is that dy by dx is equal to dy by dz into dz by dx. You can see it's a chain of two links. One link is y with respect to z, and the other link is z with respect to x. So we are establishing the link between these two. Okay, so now substitute this. So this is differentiation of now y with respect to z was e raised power z. Okay, so this term multiplied with dz by dx, and z is sine x. So that is differentiation of sine x. Okay, so this becomes e raised power z into sine into cos x. Differentiation of sine x, you can see, is cos x. And the third step is the resubstitution. I cannot leave the answer in terms of z because z is a dummy variable. So I have to resubstitute z. Okay, so step 3 is the resubstitution step. So what I have to do? I have to resubstitute the value of z as sine x over here. This is the resubstitution. So that will give me that dy by dx, and I'll write this more conveniently as cos x into e raised power z, which is e raised power sine x. So this is the first thing. This is the derivative in general. Now next thing is, I wanted to find the value of the derivative at the point x equal to 0. So that is nothing but the value of dy by dx when x is equal to 0. So that becomes how much? That becomes cos 0 into e raised power sine 0, which is nothing but cos 0 into e raised power 0, which is nothing but 1 into e raised power 0, which is nothing but 1. So your answer finally is this, that the value of the derivative at the point x equal to 0, or if we have drawn the graph, the slope of the tangent at the point x equal to 0, in fact, happens to be 1.
Yes, sir. Got it.
Okay, so don't worry if it takes you time to work out all these steps initially. Okay, we are absolutely, time is not the issue initially when we are doing these type of things. Okay, what is the thing is that we should understand each and every step carefully, and we should avoid making any mistakes while doing the steps. Speed will automatically come. We'll make you do so many questions that the speed will come. Okay, let's come back to the worksheet. So this is clear now?
Yes, sir.
Okay,
Yes.
very good.
So now the fifth question.
Okay, I'm just going to the worksheet once. Okay, we'll go through it. So first question, any other part you have a doubt in? No, no?
No, sir.
Okay, so you can see that you have to identify in which question what method you have to use. For example, second question you have to use the quotient rule. Third question you have to use the product rule. But D part and E part you are using the chain rule method. Even A part you are using the chain rule method. Okay, second question, any doubt with any of the parts?
So I don't have a doubt, but I wanted to confirm that in A part, y is equal to sine square x plus cos square x. So can we do it like y is equal to 1? So differentiation.
Yes, very good. That's the simple way of doing it. Now. This is like that Alexander knot wala problem. You know? Everybody was trying to open the knot and nobody could. Alexander just took out his sword and cut it, and the problem was solved. Okay, so it's like that. So we know that trigonometrically sine square x plus cos square x is equal to 1. So therefore y is equal to 1. So it's enough to say that that means differentiation of y with respect to x is 0. However, you can also check by chain rule that differentiation of sine x, or rather sine square x, will come out to be 2 sine x cos x. Okay, and if you differentiate by chain rule cos square x, it will come out to be minus 2 sine x cos x. So that will also show you that differentiation of sine square x plus cos square x will give you 0. But that is like a very lengthy way of, or you can even say that that is a way of proving that if you wanted to, for example, use calculus to prove that sine square x plus cos square x is a constant. So first you differentiate this and show that it's 0. And then for its value, you can just, once it's a constant, you can just take some arbitrary value of x and find that constant. So take x as 0. So it is 0 plus 1. So the value is 1. So we know that it's a constant whose value is 1. Okay.
Can we use
But yeah,
product
in
rule
this case,
sin x
since
into
I'm,
sin x?
yeah, sorry, beta.
So can we use product rule for like sin x into sin x plus cos x?
That also you can do. So this function is one of those unique things where you can use chain rule also. So first method is you can substitute z as sin x and substitute y as z square and then use chain rule. Okay. Or you can also do this, that you can express y as sin x into sin x and use product rule. So derivative of y will become sine derivative into sine plus sine into sine's derivative. Okay. So that is 2 sin x cos x. Okay. And I'm not sure if you've learned in trigonometry yet that 2 sin x cos x is also equal to how much? Sine 2x.
Sine 2x.
Sine 2x.
Have you done the formula of sine a plus b and cos a plus b and all this?
Yes.
Yes.
Sine a cos b plus cos a sine b and all that. Okay. So
Sir,
if you've done
Hemant sir
those,
ne kara hai.
okay, very good. So if you've done those, now you can even try doing the proof of differentiation of sine x and cos x by limit method. Okay, that differentiation of sine x is limit delta x tending to 0. Okay. Sine of x plus delta x minus
So this
sine
was
x.
done by Hemant sir. He
Achha, you've done-
illustrated this.
He illustrated this. Okay, so you can use that along with the, so you can try all these things out also. Okay. Okay. Anything else in the second question? Oh, sorry, third question we were at. So third question, you have to clarify this. So yeah. So as far as this question is concerned, you can directly write it as 1 and show that it's a constant. Okay. But for example, if some question asks you to prove that this is a constant using calculus, that would be a nice way to prove that. Okay. Any other part of second question?
Sir, the E
No,
part.
sir.
No, sir.
Yeah. Sorry, somebody was saying which one?
E part.
E part. Okay. Achha, now before I come to E part, also you can see in some of these you have an option like ln x by x. You can treat it as a product of two things, or you can treat it like the quotient of two things. So you can see that differentiation of y will become denominator into differential of numerator minus numerator into differential of denominator divided by denominator square. You can do it this way also. So it is 1 minus ln x by x square, or you can also prove it like a product rule. So 1 by x is differentiation, you know, is minus 1 by x square into this plus first function into derivative of second function, which is 1 by x. So you can see it is minus ln x plus 1 by x square, which is the same thing. Okay. So you can even show that it's equivalent by both the methods. This is by product rule. This is by by quotient rule. Okay. So that is okay. All right, let's come to this one, last one. So here we'll have to use the quotient rule. So dy by dx will become denominator into differential of numerator minus numerator into differential of denominator divided by denominator squared. So that will be 1 plus x square into derivative of x minus 1, which is 1. Okay. Minus x minus 1 into derivative of 1 plus x square, which is 2x. Okay. The whole thing divided by 1 plus x squared to the power 2. So this becomes now how much? This becomes 1 plus x square minus 2x square plus 2x divided by 1 plus x square whole square. Okay. So it becomes like this: 1 plus 2x minus x square divided by 1 plus x square whole square. So this is your dy by dx.
Okay, sir. Understood.
Okay. Now, for example, you want to find the slope of tangent at x equal to 0. Just substitute x equal to 0, you will get the answer. At x equal to 1, you substitute like that. Okay.
Yes,
All
sir.
right. So third question. Okay. Fourth question. Oh, sorry, there are two third questions by mistake. So the second, third question, anybody has a doubt? I think that's a very direct question, so no problems with that. Then fourth question, what should actually be the fifth question, but
Yes, sir. Can you do the fourth one?
Fourth one, okay. First of all, unfortunately, the print has not come through properly. This should be, I think this should be 2 pi by 3. So that this point was actually 120 degrees. This point was 135 degrees. This is 150 degrees. And finally, 180 degrees. Okay, so let's spend some time on this question. So for whatever reason, this 2 pi has not come through. This was also the same. So this is part of analysis of functions by differentiation, something that we'll be learning moving ahead also when we discuss about something called maxima minima. Some of you might have heard about the term maxima minima or local maxima minima, etc. So I'm just switching to my whiteboard. Okay. So if you look at the function y is equal to sine square x. Okay. Now, without getting into the values, if you were to just analyze the graph using the knowledge that you already know the graph of y is equal to sine x. Okay. So you know the graph of y is equal to sine x looks like a wave. When you look in one full cycle, it looks like a wave, something like this. So these are the most obvious points to consider for y equal to sine x graph. But also some important points are, for example, here at pi by 4, that is 45 degrees, the value is nearly 0.7 or 1 by root 2. Okay. And that value again repeats at 3 pi by 4 or 135. Okay. Similarly, at 5 pi by 4 or 225 degrees, the value becomes minus of 0.7. So 0.7 is approximately 1 by root 2. And again, that value repeats at 7 pi by 4 like this. Okay. Also, if you consider, for example, pi by 6 or 30 degrees, the value is exactly half, 0.5. And again, that repeats over here at 5 pi by 6 and so on and so on. Now you think what happens when you square this graph. So when you square this graph, of course, the negative side comes up, okay, but also these values change. At pi by 2, the value remains 1 because 1 square is 1. But for example, at pi by 4, the value becomes nearly 0.5 because 7 sevens are 49, so 0.49, or exactly it becomes 1 by 2. Similarly, at pi by 6, the value becomes actually 1 by 4 because it's 0.25. Okay, so logically, without getting into actually calculating the values, if we just think about how this graph looks by just squaring this graph, squaring this earlier graph, how does the graph of sine square x look like? So it will first of all not have a negative part. Okay, it's like the negative part will get reflected up, and secondly, even the shape of this curve will change because the value is in between 0 and 1, and then again between 1 and 0 they are changing because they are getting squared. Okay. So that is just a matter of observation. It's not really part of what we are doing in differentiation or anything, but it's just a matter of, so since we are talking about functions a lot, okay, so this is part of the observation of a function, how the graph can be generated. So you can see that sine square x graph will look something like this. I'm not drawing it exactly to scale with respect to the one below, but so instead of varying between 0 and between -1 and 1, it will only vary between 0 and +1. So the so-called cycle of the graph now becomes pi instead of being 2 pi because you're squaring it. Of course, I had asked you in the question only to plot between 0 and pi. So just this first part was required. But also these values in between are changing. So now you can see that at pi by 4, the value is actually 0.5 instead of being 1 by root 2. It's exactly 1 by 2. At pi by 6, the value is exactly 0.25. Okay. And then again, that value will repeat at 5 pi by 6. Oh, sorry, this will be, yeah, 5 pi by 6. Okay. And then again, that will repeat over here at 7 pi by 6. And then again, that will repeat over here at 2 pi minus pi by 6. So that will be 11 pi by 6. Okay. Similarly, this value will repeat at 3 pi by 4. And again, it will repeat over here at 5 pi by 4. And again, it will repeat over here at 7 pi by 4. Yes, Nishchay, you have a question, beta?
Sir, how to know that at what interval it is getting repeated? Is there a formula for that?
See, one is you have seen the circularity or trigonometric function, no?
Yes, sir.
So you understand how this repeats, no? Why it repeats in a cycle of 2 pi?
Yes, sir.
Because if you take this as theta, then your sine x, sine theta is basically just the ratio of this perpendicular upon this hypotenuse. So when you complete one full circle, the values repeat after that. Okay. Now it's observation that when you square this, you can see that this lower part is just getting mirrored above, no? And the shape of the graph is changing a bit. So you see how the periodicity is changing?
Yes, sir.
So that is the thing. Okay. So this is what from observation we can say the graph looks like. Okay. And of course, I'd also asked you to find out the values. So you could have plotted the values and made this graph also. So for example, if you are making the graph with the very traditional method of just plotting, so you have the function y equal to sine square x and just use the various points I've asked. So x equal to 0, you calculate y is equal to 0. X equal to pi by 6, that's 30. You calculate y is sine square 30, so that's 1 by 4 or 0.25. So like that, you plot all those points. Okay. And once you have got all those ordered pairs, you plot those points between 0 and pi, and you'll see that you will get a shape like this.
Sir, so we can take pi as approximately 3.1 or like that, right?
Sorry, we can take y as?
Pi as 3.1 and then mark it on the graph, right?
Exactly. You know, we can mark it on the graph like that. Okay. Now the next thing is we wanted to understand the slope of the tangent at various points on this graph. Okay. So slope of the tangent, you'll again get, you can either use product rule or chain rule, whichever you want. So I'll go with chain rule. So for dy by dx, the same method that you substitute y as z square, where z is equal to sine x. So dy by dx becomes 2 sine x cos x. Or what we also know is equivalent to sine 2x. Yes, Nishchay?
Sir, like if the x is in degrees, then the graph will be different, right?
The graph will be different in the sense that how we show the variation on the x-axis will be different. It is like, you know, even if I plot a graph of y is equal to, suppose I plot x square, this graph only, okay. And in one case, I'm taking my scale such that one box on the x-axis is equal to 1 unit. Then the shape of the graph will be something like this, let's say. Okay. So if this is 0, this is 1, this is 2, this is 3, this is 4, this is 5, like this. Okay. So on the y-axis, this is also 1, this is 2, this is 3, this is 4. So this graph will go through this point and then this point and then some point much above. So the shape of this graph will look something like this. But if somebody else decides that, okay, no, for them, the y-axis is the same. So it's these points only. But for them on the x-axis, this point is 1. Okay, instead of these points. This point is 2. Sorry. Just 1. So they decide that 2 boxes are equal to 1 unit. So this point is now 2. This point is now 3. So for them, what will happen? The point on the graph will be this one. The next point will be this one. The next point will be somewhere way above here. So for them, the shape of the graph is changed. So the
So it
exact
will
shape of the
change,
graph
right?
also depends on how we take the values on the x-axis and y-axis, no? How we take the scaling of the graph, what we call, right?
Yes, sir. So it will
Understanding
be different for x if it is in degrees as compared
so
to
that
what we
depends on
got
how
in
we are
pi.
taking the scale, na? So see, it's not that just by changing from degrees to radians, the graph is going to change. If I take the scale equivalent, then it's not going to change. You're getting my point now? If I take one box as pi by 6, but that one box is also equivalent to 30 degrees, then there's no difference at all. No? It'll be the
Okay.
same. You're
Yes.
understanding the point? No?
Yes.
So on the same graph, I can show the same points both in degrees and radians, right? It makes no difference at all because they're equivalent. So if I'm making a slightly more exact graph now, let's say, okay, and my y versus x is like this. So let's say I've just plotted in one cycle, that is 0 to pi. Okay, and roughly it is like this. Now it's a matter of my choice of units. You know, I can express this point as pi by 2. I can also express this point as 90 degrees. But as long as both of us have taken the same scale, that so many boxes is pi by 2 radians, or the same number of boxes is 90 degrees, it makes no difference because then this point will become pi, which is equivalent to 180 degrees. Okay.
Yes.
And this point, so this point will become pi by 4, which is 45 degrees. Okay. This point will become, let's say, 3 pi by 4, which is 135 degrees. Okay. So for example, this point here will be 5 pi by 6, because I'm taking this as 150 degrees, and similarly this point here is pi by 6 or 30 degrees. Okay. So the values we had seen earlier also. Now I'm talking about the slopes. Okay. So this was 0.25. Okay. This was 0.5. This was 1. Now let's talk about slope. Slope of tangent. So that is the value of dy by dx. So slope of tangent at x equal to pi by 2, for example, you can see is sine 180, you can write it as, or 2 times sine pi by 2 cos pi by 2, which by definition I know is 0. So how that is making sense in the graph, you can see that if I draw tangent at the point x equal to pi by 2, you can see that is the point where the graph is exactly curving like this. So if I drew two consecutive points at that point and joined them, it would tend to be a horizontal line. You're getting an idea from the symmetry of the graph, because up to 90 the curve was going up, and after 90 it started coming down. So that means exactly at 90, if I draw the tangent, it should be a horizontal line. Yes, Abhinav?
Sir, this is that maximum and minimum, no?
So later we will see this is the concept of maxima and minima, because यहाँ पे slope 0 हो जा रहा है 90 पे. That means exactly at 90 only it should reach the peak, because before 90 at any point if you draw the tangent, you'll see it's having a positive slope, and after 90 it's having a negative slope. So that means the function was increasing, then reaching the peak, then decreasing. So when we discuss about maxima and minima next as application of derivative, we will see that this is the concept that we apply. So we can see that at x equal to 90 degrees or pi by 2, the slope of tangent is equal to 0. But similarly, if we now check the slope at x equal to pi by 4, you can see that that will become sine 90. That's in fact 1. Okay, so that's, or 2 sine pi by 4 cos pi by 4. So that is 2 into 1 by root 2 into 1 by root 2. So that's plus 1. So you can see that when I draw the tangent here, it's having a positive slope. But by symmetry, you should also see, because this half and this half are like mirror images. So if this is having a slope of plus 1, then at this point, which is symmetrical, if I draw the tangent, it should have a slope of minus 1. And that is what we can check with the values also, that if you now put dy by dx at the point x equal to 3 pi by 4 or 135 degrees, you'll get 2 sine 3 pi by 4 cos 3 pi by 4, or you can also write that as sine 3 pi by 2 using the sine 2x formula. But you know that sine in the second quadrant is positive, but cos is negative. So this will become minus 1. So as expected, you can see that the slope is minus 1. And that way you can check for these 2 points also. You will see there are symmetrical slopes, but this side is a positive slope, this side is a negative slope, and a different value compared to these two. So basically, I gave you this question with so much work in it that you plot the points, draw the graph, draw the tangents on it, so that you intuitively understand these things about a function, without getting into the technical language of what is maxima, minima. That we'll see. No point, no worry about that. But through this, now you can experience from your own understanding of these, when you go over it point by point, okay, in detail, how the relationship of the function with its rate of change, how it shows us something about the graph, how the relationship of slope at 2 different points which are symmetrical, the values are symmetrical. Yahan pe +1 hai, yahan pe -1 hai. So that symmetry is showing up in the graph also, in the shape of the curve. So these are all things that we can, very interesting properties of functions, etc., that we can learn by just studying the derivative of the function. And that is the full scope of the subject of calculus. It is not just that we can calculate instantaneous velocity from displacement or instantaneous acceleration from velocity. Yes, of course we can do that in physics, but we can do so much more, and that is part of the analysis of functions. Anyhow, so hope this question is clear.
Yes, sir.
Yes, sir.
Okay, couple of messages. Yeah, Nishchay, that's correct about the maxima. Anirudh, let me understand your question. The value of sine and cos is between 1 and -1. So the slope of the sine and cos function is also between, yes, that is correct. So if you look at the slope of the tangent, further if you look at dy by dx, is when you reduce it, it's sine 2x. So you can see that sine of anything, it has a range. It cannot be less than -1. It cannot be greater than +1. So what is that telling us? That the slope of the tangent in this graph, its minimum value is -1 and its maximum value is +1. No matter what values of x I take over all the cycles, the slope will always range between -1 and +1, including these two values. So the steepest positive slope it will have is of +1. The steepest negative slope it will have is of -1. And that you can see in this kind of in the shape also here. If you shift from this point to this point, the steepness is becoming less. If you shift from this point to this point, again you can see the steepness is becoming slightly less. It's almost as if you can see it in the perfect graph, that this point in between should have the maximum slope. Okay, let's just go over the worksheet once more. So that is question number 4 done. Okay. What about question number 5? Any doubts in that?
Yes, sir. This question.
Yes.
Okay, so question number 5 is like a direct application of rate of change in a practical situation. Okay, you can say it's a physics situation because it involves physical parameters like mass of gas, okay, rate at which gas is. So whatever reason, okay, stick to this only. So what is the information given in the question? Let's understand that first. So the gas is, the cylinder is initially empty, okay, at time t equal to 0. So that's the first thing we can start with, that the mass of gas is equal to 0 at t equal to 0. But we are pumping in gas, plus there is some leakage also happening. That means in general, mass will be some kind of function of time. Okay. Why it will be a function of time? Because we are changing the mass. How we know we are changing the mass? Because we are involving a process which is about pumping in the gas, and we are involving a process which is about leakage of the gas. So both the things are happening simultaneously. So in general, we are filling as well as gas is leaking out. So that means the mass must be changing with time. But initially the mass was 0. Okay. So this is the first thing that we understand, that mass is a function of time. Okay. Now if we talk about the rate at which mass is changing, the rate of change of mass, instantaneous rate of change of mass with respect to time. So that we can write as dm by dt. That instantaneous rate will be logically what? It will be the rate of inflow, okay, via pumping, you can say, or the rate of pumping in gas minus the rate of leakage. This makes logical sense.
Yes, sir.
Okay. Now the rate of inflow, that is a variable quantity. Okay. So the rate of change of mass with respect to time is the rate of inflow, which is a variable quantity, which just means that from time to time it changes. At t equal to 0, it was 4 grams per second. But by the time the time is 1 second, I've increased the rate to 5 grams per second. By the time it's 10 seconds, I've increased it to 14 grams per second. Okay. Whereas the rate of leakage is constant at 2. So the rate at which mass of the gas in the tank increases as a function of time, that is simply the algebraic sum of these two, so that it becomes 2 plus t in grams per second. So in spite of the leakage, you can see the rate at which inflow is happening is always dominating compared to the rate of leakage. So dm by dt is always a positive quantity. Now from t equal to 0 onwards, you can see it's positive. It's never less than 2. So the mass of gas in the tank must be increasing all the time. And how it's increasing with time? It's increasing like a function like this. Okay. So hope this much is clear. Then we'll come to the second part.
Yes, sir.
Okay. So now see, from this what information we've got, that not only we know that mass is a function of time and all that, we know how mass is changing with time. It's changing according to the function. So from this we have learned that mass is a function of time such that the rate of change of mass with respect to time is a linear function. It is t plus 2. So now this is, think of it like a calculus problem. I know dy by dx is x plus 2. So this is a linear function. No? That means y must be which type of function? It must be a quadratic. So we can again go by that method instead of using integration, which we haven't learned yet officially. So I'll just say that, okay, y is equal to ax square plus bx plus c, such that dy by dx, it should be 2ax plus b, is actually given by this term, which is x plus 2. So that concept we'll use, but in the language of mass and time now, instead of y and x. Okay. So instead of using this dy by dx thing, we'll just understand that here m is a function of time such that dm by dt is a linear function. Okay. So the moment we have understood that m is a linear function, sorry, dm by dt is linear in time. So what that tells us, that implies that m must be a quadratic function. It must be quadratic in time. So now we can proceed by a normal method, that let us assume m as a function of time is some at square plus bt plus c, where a, b and c are constants which we don't know. Okay. Now the first information even before this that I had was that m is equal to 0 at t equal to 0. So use this information now. Okay. So this is such that m is equal to 0 at t equal to 0. So that tells me, okay, c must be 0. Okay. So the moment c becomes 0, now you can see that differentiation of this becomes (280) plus b plus c, but c is already 0, so it's 280 plus b. So this dm by dt, oh sorry, c is not going to come in the differentiation, so don't use that. So now compare this with the given information. So compare this equation with this. So we can see that 280 plus b must be equal to t plus 2. That means a must be equal to 0.5 and b must be equal to 1. So the mass as a function of time is therefore now becoming how much? I've got the value of a, I've got the value of b, I've got the value of c. So that means mass as a function of time is
Sir,
0.
B is 2, right?
Sir, B is 2, right?
Oh, sorry. Yeah, b is 2. Correct. So it is this plus 2t. So this is the mass as a function of time.
Understood, sir.
Okay, understood now. So this is just to get you used to now gradually what we are going to do in future chapters, how we are going to use calculus in an actual physics problem. So this is one example of that. Okay. So we've discussed quite a few examples to this. Okay. I hope you have also worked out questions from the module.
Yes,
At
sir.
least the questions which I have asked you to solve it. Okay.
Yes, sir.
All right. Let's do some examples of application of chain rule now. Okay. we'll take some extreme examples, some more tricky type of examples. Okay, just give this a try. It should not take you more than few minutes. We'll discuss.
Are done.
Done.
Okay, so I'm receiving some of the answers from all of you. So I'll just put up the answers directly first so you can verify. Then we'll discuss steps, whether we can use some shortcuts and things also.
So my first answer is not the same as yours.
Okay, so
Sir,
let's check
mine
out.
also.
Sir, my also.
Mine also.
Okay, let me check out. Okay, so let's go over the steps of the first one. So there are two ways we can do this. One is we can first simplify this. Okay, now ln of a to the power n is n ln a. We can do that. Okay. So that is one step. So we can write this as 1 by square root of,
Sir, the ln x square is in the numerator, not in the denominator.
oh sorry, it's in the numerator, right? It's square root of ln, right, x square. Anyhow, you understood the simplification step, I'm sure that instead of starting with chain rule, what we can do is we can first simplify this as square root of 2 ln x. Okay, thereby taking the square root 2 as a constant outside. Okay, like that. Now what we can do is, so this is basically root 2 multiplied by root of ln x. So that's one method. Okay, so now what we can do is you can take ln x as z. So y is equal to root 2z. So dy by dx as dy by dz into dz by dx. This will become root 2 into 1 by 2 root z, okay, into dz by dx, which is 1 by x. That is how I think I got. This is what I had written as the answer earlier also.
Yes, sir.
Okay. So this was my logic initially. Okay. However, if you have not done this step, if you have not converted this using this property, you can still go, but it will just be a little bit longer. So you can also do like this, that. So what you do is substitute ln of x square as, let's say, z. Okay. So y becomes square root of z. And further in this, make another substitution. Substitute x square, let's say, as u. So z becomes ln u. So it is like, here what we have done is on x, we have first operated square to get x square. Then on that we have operated ln to get ln x square. And on that we have operated square root to get square root of ln x square. Okay. So basically this is our y, which is square root of z. This is our z. This is our u. So z is ln u, like this. So we have two substituted variables. So here if I use chain rule, become like this, that dy by dx is now, see, y is expressed as a function of z. This one. So this will be dy by dz. Okay. But z itself is ln of x square, where, okay, so z is a function of u. Okay. And then further you can see that u is a function of x. So it is u is like h of x. So y is like f of g of hx. X. Where h is the whole square function, g is the ln function, and f is the square root function. This is a very complicated way of looking at things, but so this is dz by du into du by dx. So this will become differentiation with respect to z of ln z, oh sorry, of square root z multiplied with differentiation with respect to u of ln u multiplied with differentiation with respect to x of x square. Let's see what this will give us. So 1 by 2 root z into 1 by u into 2x. So now let's do the resubstitution. So 1 by 2 root of ln u. And now let's substitute u as x square. Which we can also write as 1 by x. So these two are interchangeable. So this is a more complicated kind of extreme example of application of chain rule. So before I come to this thing, this can also be written as, now see, 2 ln x is the same thing as ln x square. So that means I can also write dy by dx as 1 upon x square root of ln of x square. You can also write it like this. So the two are equivalent.
So that is a logarithmic property.
That is a logarithm property. For log, you should remember these properties, that ln ab, for example, is ln a plus ln b. Okay. ln a by b is ln a minus ln b, and natural log of a to the power n is n times natural log of a. You can use ln and log to any base alternatively. It will work for log of any base also. Okay. So if I use this property of log, then I'm saved from the struggle of double substitution. A single substitution is enough over here. So you can see the number of steps are considerably less compared to the double substitution. So I'll just give you a minute to go through both the methods. Okay, so this is method 1, where I've simplified this first. I've simplified using this property. Okay, and then I've used chain rule. Whereas here I've not simplified. I've directly gone into like a brute force method of substitution without simplifying that first. Yes, so most of you got the other parts correct, okay, without any difficulty. Yeah, students, sorry, I got disconnected in between. So let me share the screen again. Okay, I think somebody else is the host currently. Can you just make me the host again?
Sir, you are
Oh,
only the host.
Okay, my second one is the host. Just a minute. Okay, we should be back online now. Okay, so hope all of you understood the first method of doing this question, which is by the simplification, that you first simplify ln of x square inside the square root as 2 times ln x. Okay, so that square root 2 is just a constant, and with a single substitution. Okay. Now let's come to the second method, where if we did not simplify it, you'll see that things become a little bit more complicated, because then we have to do this kind of substitution. It is square root of ln of x square. So from x we are first operating whole square function. Then on that whole x square we are operating the log function ln of x square. And then on that log function we are operating the square root function. So it is square root of ln of x square. So we have to do a double substitution. Okay. So x is first converted by whole squaring into x square, which will take, let's say, as u. Okay. Then we are taking the ln of that. So that is becoming ln of x square, or that is the same thing as ln of u, which we'll take as z. And then on that we are operating the square root function. So we're getting square root of ln of x square, which is basically square root of z, which is basically square root of ln of u, like this. So we have these two substitutions, that u is equal to x square. So z is equal to ln u. So finally y is equal to square root of z. So these are the substitutions that we use. That's why our chain rule has this now. Has these three terms. Okay, so people hope this second method is also clear to all of you.
Yes.
Yes, sir.
Okay, all right. Now the other parts you had all got the answers, I think. Just check once.
Yes,
Yes, sir.
sir.
Second, third, and fourth, all of you got the answers.
Yes, yes.
So this is, I mean, with this kind of technique and these kind of different methods and all, you should be able to differentiate any and every function. Okay.
So could you please show the answer for third one?
Sorry, come again, Vita.
Sir, could you please show the answer for third one?
Third one, okay, this one. Yeah, you can write it as 2 sin x cos x into e raised power sine square x, or you can further simplify it and write it as sine 2x multiplied by e raised power sine square x.
Yes, yes, sir, I got. But if I leave it in the first stage of it only, like the first statement she wrote,
Sorry,
like,
which one?
sir, I'm saying that if we leave it at 2 sin x cos x into e to the power sine square x, is it okay, or do we?
No, it's fine. No? You can leave the answer this way also. Okay. But the thing is, you must know how to simplify, because remember, ultimately in the exam, you might have MCQ question. No? So the option might be given as this instead of the first one. You should know that this is equivalent to this. Okay. So as I said, with these kind of techniques, you should be able to differentiate any kind of function that you are required to do, especially at the physics level. Now let us look at some application types of problems of differentiation. Okay. Before we come to maximum minima, let's look at some application examples. So the first type of application example we look at is when we are basically directly applying chain rule. In a physics problem. Okay. So basically what is happening is, let us say that y is a function of z and z is a function of x. Okay. And we know how x is changing with respect to time. So how do we find how y is changing with respect to time? So we use chain rule. That rate of change of y with respect to time is rate of change of y with respect to z into rate of change of z with respect to x into rate of change of x with respect to time. So very simple example of this would be something like this. We have a spherical ball of dust, let's say, perfectly spherical ball of dust, okay, which is increasing in size, okay, because it picks up dust from suspended particles of air. So we have a spherical ball of dust which is increasing in size such that its radius, let's say r, increases uniformly with time. Okay. At the rate of let's say 2 millimeters per second. So just imagine this situation. We have a spherical ball of dust which at some time t has a radius r, but as time is progressing, its radius is increasing. So at a time t plus delta t, its radius has become r plus delta r, such that we know that the rate at which the radius is increasing is a uniform rate of 2 millimeters per second. Okay. Now from this information, what we want to do is we want to find out the rate at which its surface area changes. Increasing at an instant when the instantaneous value of radius is, let us say, 5 centimeters. So we'll see that we'll be applying this concept over here. that surface area is a function of radius and radius is changing with respect to time. Okay. So think of surface area like one variable S. S is the function of R and R itself is changing with respect to time. And we'll do a second part of it where we'll see that you have to calculate the rate at which the volume is changing with respect to time. Again, the same thing. At an instant when the instantaneous radius is equal to 5 centimeters, same instant. Yeah, Vedant, your answers seem to be correct. Mansi, I'll just check your answer seems to be correct. Nishchay, your answer must have a figure of pi somewhere. Okay.
Yes, sir. I forgot to write.
You forgot to add the pi. Okay. Okay, so here we can just simply use the simple idea that surface area S is equal to 4 pi r square as a formula. So rate of change of surface area ds by dt will be equal to rate of change of 4 pi r square with respect to time. So basically we can write rate of change of surface area with respect to time as rate of change of surface area with respect to radius into dr by dt. Okay. So this is our chain rule concept. Okay. And from this fact, we can see that radius is changing at the uniform rate of 2 millimeter per second. So that will be substituted here. So this will become differentiation with respect to r of 4 pi r square into dr by dt. So that is 4 pi into 2r into dr by dt. So as a relationship, we can see that rate of change of surface area is going to be 8 pi r into dr by dt. And let's understand this in terms of units.
Sir,
R is in, yeah.
so we have to do dr square by dr also, no?
वही क्या ना तभी तो ये 2 आ रहा है ना. Okay. You see differentiation of 4 pi r square with respect to r again. So that is 4 pi into differentiation of r square with respect to r. So that is 4 pi into 2r. So this step is done over here. You can see.
Yes, understood. Yes.
Right? Okay. So now see r will be in centimeter or millimeter, whatever. dr by dt will be in millimeter per second. So ultimately ds by dt will be in millimeter square per second, or we can change it to centimeter square per second or whatever. So that is how the physical units also work. Okay. So at the instant when r is equal to, what was it, 5 centimeters. Okay, this should become 8 pi into 5 centimeters into, this was how much now? 2 millimeters per second, right? So 2 millimeter per second. So that is becoming, you can call it 80 pi, okay, into 10 raised power minus 1 centimeters square per second, okay, or 8 pi centimeters square per second. Or we can also say that it is 800 pi millimeter square per second. Okay. Or we can even express it in SI unit and say that it is 8 pi upon 100 to the power 2 meter square per second. Whatever we want to express the unit in, it's fine. But this is the rate at which the area is increasing. The surface area is increasing with respect to time. So this is the differential calculus method of doing this. Okay. Now I'm going to just show you a very interesting geometrical method of doing this also. But okay, let's just make sure that we are clear with this first of all. And then very similar method you apply for the second part, the volume part. So in second part, you can express the volume simply as 4 by 3 pi r cube. So again, you can see that rate of change of volume with respect to time will become rate of change of volume with respect to the radius into rate of change of radius with respect to time. Yes. Yes. Tell me, madam.
So this volume one, sir, answer will be 20,000 pi.
Okay, let's check out the answer. So this will become differentiation with respect to radius of 4 by 3 pi r cube into dr by dt. Okay, so this will be 4 by 3 pi into 3 r square into dr by dt. So that will become 4 pi r square dr by dt. So this is our volume rate. Okay, now we have to find at the instant when r is equal to 5 centimeters, and of course this is changing at the rate of 2 millimeters per second. So that will become 4 pi into 25 into 2. And if we are writing in centimeters per second, we can just take 10 raised power minus 1 in centimeter cube per second. So that's 20 pi cubic centimeters per second. Is correct? You're getting the same value?
Sir, I got 20,000 millimeter cube.
Millimeter
20,000.
cube per second. No? You would have got
Ah.
20,000 millimeters. So that's the same thing, right?
Yes, sir.
Because 20 pi centimeter cube will be 20,000 pi millimeter cube. No? So that's equivalent to this thing into 10 raised power 3 in millimeter cube per second. Okay, so that's this amount, guys.
Sir, in the volume part, r
Yeah.
square is r cube is a function of r. No, so we will also have to do dr cube upon dr.
हाँ तो वही किया ना. See this step ना is that only ना. You differentiate.
Sir.
Sir, your screen is frozen.
Yeah, so just sharing the screen again. So you power cut at my place, so very heavy rainfall must be the same, at least in Thane. Okay, so Abhinav, I think you had this doubt, right? Differentiating
Yes,
of.
sir.
So you've seen that we are doing that, na? Yeah. This 3r square has come from differentiation of r cube only, na?
Yes.
Okay. So basically, when we are differentiating with respect to time r cube, we'll get differentiation with respect to r into d by dt. That's how we are getting this term 3r square into dr by dt. And the 4 by 3 pi is just a constant, it's coming outside. So
Yes, sir, understood.
So this is a direct application of chain rule, as you can see. Okay. Now, as I said, that there's another interesting way of analyzing this question, and that is by the limits method. We can do like this. That what is happening is that if you look at the sphere at some time t, and say that okay, its radius is r, and then after some time we look at it, and its radius has increased to r plus delta r at time t plus delta t. So we can see that at t equal to t, my surface area was 4 pi r square. At t plus delta t, my surface area became s plus delta s. It increased by some factor of delta s, which is 4 pi r plus delta r whole square. So now my instantaneous rate of change of surface area will be delta s by delta t, but with a limit delta t tending to 0. So when delta t tends to 0, basically delta t becomes dt, right? So dr becomes delta r becomes dr, like that it will become. So this will become 4 pi r plus delta r whole square minus r square divided by delta t, but with that limit. Okay. So as you can see, it will become that only. It will become that becomes 8 pi r dr by dt. So this is the way to logically understand how we have implemented differentiation, because ultimately differentiation comes from rate of change by first principle, that it's for a very small change. So everything ultimately is coming from the basic definition of instantaneous rate of change, that ds by dt is nothing but delta s by delta t under the limit that delta t should be tending to 0. It's coming from that only. Yeah, actually, there's very heavy rainfall in my part of town, so there'll be a bit of issue with internet connectivity. So my voice might be breaking in between, but I'll send you the recording. And in case we are coming to the end of the lecture, so okay. Now let's look at the volume situation. That's even more interesting. We can do that volume question actually like this: that at some point of time t, the radius is r, so the volume is 4 by 3 pi r cube. Okay. Now at a time t plus dt, let's directly take dt only. We are adding a thin layer of volume. So this thin layer is being added. So this thin layer has a thickness of how much? dr. So the radius has become r plus dr. So the volume has become v plus dv. Okay. Now that dv is the volume of the thin layer added. So that thin layer is of thickness dr. So what will be the volume of that thin layer? It will be surface area into thickness. Does this make sense, people? Yes.
Yes, sir.
Yes, sir.
Sir, can you
Surface
repeat?
area उस instant में कितना था? 4 pi r square था. Okay. And thickness कितना है? dr है.
Sir, can you repeat?
See, just see this shaded part. Na? It's a thin layer. It's like a thin shell. So that thin shell has a thickness of how much? dr and a surface area of how much? 4 pi r square.
Yes, sir.
You understanding now? So it's like we have taken a sheet which has surface area of capital S and of thickness dr, and we have put that sheet, we have wrapped that sheet around that ball, right? So how much volume we have wrapped around? This is the volume we have added. Surface area into thickness. So surface area is 4 pi r square, thickness is dr. So therefore the rate of change of volume is nothing but divide this by dt. So it's 4 pi r square dr by dt. So it is the immediate surface area multiplied by the rate at which this is changing, which we just saw. And this was the formula for rate of change of volume, which we had seen by chain rule also above. See, this is what we got by chain rule also. So this is another way to understand it geometrically or logically, that is what is happening. But if you look at the volume of that ball, it is increasing by a very slight amount in time dt. And that slight increase in volume is the shaded portion in red, which is like a thin shell. It's a thin spherical shell of radius r and thickness dr. So that is the volume that has been added. Right. So hope this is clear, people.
Yes, sir.
Yes, sir.
Okay.
Sir, so in general for sphere also we can say that it is the volume is 4 pi r square into the thickness of the material, right?
No, but then see, for the full sphere, na, the radius is varying. Na? Like if you have a thick shell, if you have a thick spherical shell like this, so the inner radius is a and the outer radius is b. So if you want to use a formula like this for surface area into thickness, what is the surface area you take? Because you know the radius is varying between a and b. No?
Okay, sir.
Okay, so later we will see that we can calculate the volume of a shell like this by doing something called integration. You know, we will slice this sphere into thin shells like this, where each shell has a very small thickness of dr and has some instantaneous radius r. So that shell's thick volume is given by this formula. dv is equal to 4 pi r square into dr. So the whole thick shell, that is a to b, that volume will become integration of this from R equal to A to R equal to B. But that we will learn in integration later. Okay, so don't worry about it just now. But this method was clear, I hope, right?
Yes, sir.
Yes.
Okay.
Sir, so we can only say that for dV it is equal to surface area into thickness, not for
Yes,
other
for
large.
that thin shell we can say, correct. Only for that we can say, right?
Okay, sir.
Okay. Now, the second type of application question we will see, okay, this is the last thing we'll look at today, is when we are looking at what we call constraint relations. Okay. So what is a constraint? It is some kind of a foundation that a system has, or some kind of a limitation. Okay. So constraint is a limitation, you can say, or a fixed property of a system. So sometimes we make use of that. Okay. So for example, this is a very standard type of situation now. Okay, so this is the edge between a wall and a floor. Okay. And you have something like a thick rod which is slipping like this now. Okay. So this is a rod. Now this rod is slipping. So this point E is slipping and on the floor at a speed of, let us say, 0.4 centimeters per second. And this point B, this end of the rod, okay, so it should be just against the wall. In my diagram, it's looking like it's going into the wall, but it's okay. So this is moving at some speed VB, and let us say at this instant this angle is theta. Okay. So this is a smooth wall, and this is a smooth floor, and we have this rod which is slipping like this. So at an instant when theta is, let us say, 30 degrees, and the speed of this end is equal to 0.4 centimeters per second, we want to find the speed of the other end of the rod, which is moving vertically down on the wall. Okay, so this is a thin rigid rod, okay, in contact with a floor and wall, slipping against it. So this is what we want to do over here. Okay. So in this particular example, the constraint that we will use, there are actually a number of constraints here. One is that the length of the rod is fixed. That is the biggest constraint that you can see, because it's a rigid rod. Okay. The second is that the point E slips horizontally. Whereas B slips vertically. So these are three constraints, or these are three fixed properties that the system has. Okay. Until B loses contact with the wall, let's say that's not happening over here right now. So as it's slipping against the wall, what is the direction of the point B's motion? It is vertically downwards on the wall. Okay. Similarly, what is the direction of A's motion? A's motion is horizontally against the floor. So how we can make use of these constraints to find the unknown quantity, which is BB? Let's look at that next.
Excuse me, sir.
Yes.
So just one thing, can you explain why they would be moving at different speeds?
So that you will see now from the relation itself, you will see right now. If you just imagine this in everyday life now, you will realize that this is what happens. As the rod is slipping, you will see that the speed at which the point A and moving and point B are moving, they are different speeds.
Okay, sir.
Or you can say like this, that there is no way that we can justify that A and B should have the same speed. If I make an assumption that BB is equal to BA, there's no justification for that assumption as of now.
Yes, sir.
Right? Okay, so what we will do here is we will use these constraints along with calculus. So let's see how we'll use these constraints. So at whatever instant of time I'm looking at this, when theta is equal to 30 degrees and all that, okay, let me assume that this distance here from this fixed corner to the point A, this distance is x. Okay, and from this fixed corner to the point B vertically, this distance is y, and the length of the rod is n. So I have the relation that x square plus y square is equal to L square, where L is a constant. So I have this is my constraint. Okay, and I can see that the rate at which x is increasing, dx by dt, is equal to my instantaneous velocity of the point A. So that is 0.4 centimeters per second. Whereas the rate at which y is changing is a negative quantity, because y is decreasing with respect to time. And that should be equal to minus VB, which I don't know. Okay, so are these two equations clear? Dx by dt and dy by dt?
Yes, sir.
Okay, so now see, if I apply differentiation to this, rate of change of x square plus y square should be 0, because on the other side, the rate of change of L square should be 0, because L is a constant. Okay, so what this means is that differentiation of x square with respect to time plus differentiation of y square with respect to time should be 0. Okay, and then you apply chain rule. So I'm differentiating x square with respect to time. So that is equal to differentiation of x square with respect to x into dx by dt plus differentiation of y square with respect to y into dy by dt. So this should be equal to 0. Okay. So this step to this step, we just applied chain rule. So all of you clear up to this step?
Yes.
Yes, sir.
Yes, sir.
So now we can see differentiation of x square with respect to x is 2x. So 2x into dx by dt plus similarly 2y into 2y into dy by dt should be 0. So we have x into VA plus y into minus VB is equal to 0. So we have VB is equal to x by y times B. Okay. Now you can see that x by y in that relation was nothing but cot theta. Okay. So this is what will now justify why my VB should not be equal to VA, in fact, unless theta is equal to 45 degrees. Only at the instant when theta is 45, VA will be equal to VB. So this was whatever value I had given. Okay. I think it was 0.4 centimeters per second. Okay.
Here, so is it necessary to express it in terms of theta, or we can leave it in x by y also?
But here see, theta is given to me, xy was not given to me. So I have to solve the question according to the data which is given. Understood the point?
Yes.
Suppose I had given the length of the rod, that was 2 meters, and I told you that at that instant x is equal to √3. Okay, then you could calculate that, okay, from this y is equal to how much? 1. Okay, so that means x by y would be equal to √3 by 1. Okay, but then that would be for theta equal to 60 degrees. Okay, this is for theta equal to 30 degrees.
Sir, here it is not given that theta is 30 degree, or are you assuming?
It's given, I had given in the question. See. That was part of the question. I did not show in the diagram, but here at an instant when theta is equal to 30 degrees, VA is this much, then how much is VB? Got it now?
Yes, yes.
Okay. So I'll substitute that value here. Okay. So cot 30 is how much? Root 3?
Root 3.
Okay. So this will become 0.4 into root 3, or approximately 0.4 into 1.73 in centimeters per second. So that will be the instantaneous speed of that end B at the moment when the instantaneous speed of A is 0.4 and the angle is 30 degrees. Okay. Now, of course, why exactly this is happening, that depends on how the rod was falling. Now, from which initial position it started falling, whether somebody was pushing it or it's just falling under gravity. So that we are not concerned with. We are just given like at this moment, this is what we are observing, that A has a speed of this much and this angle is 30 degrees at that instant. So from that, what can we predict about the speed of the point B? So this is what we can predict. And this is coming from the application of the constraint relation. What are the constraints here? That one is that L is constant. The other is that A is moving along the horizontal. So therefore, B is dx by dt. B is moving vertically downwards. So therefore, VB is minus of dy by dt. So these are all our constraint relations. This, and the fact that L is constant. Okay. So this kind of application of differentiation, especially to constraint relations, is going to take us some time and experience, because we have to learn how to recognize what constraints to use in a given system, and then how to set up an equation so that we can use differentiation for that. Okay. So, however, we'll look at some practice questions in the coming week and next week, and then of course from there we will move on to more applications of maximum, minima, etc. Okay, so hope this is clear to all of you people. With this, we end today's session.
So,
Yes.
So like we took dy by
Thank
dt
you,
as
sir.
minus VB as
Thank you,
dy
sir.
by, like
Okay.
VB is along.
Yeah,
the,
Dhruv, come again, beta. Sorry, D.
Sir, I said that dy by dt is minus VB as VB is in negative y-axis, right? That's why.
हाँ, उसका रीजन देखो ऐसा है ना कि VB का डायरेक्शन ऐसा है that the quantity y is decreasing with respect to time, whereas the quantity x is increasing with respect to time, na?
Yes, sir.
No, so that's why dy by dt is negative of that rate at which y is decreasing, whereas dx by dt is a positive rate, so it's plus of VA. ठीक है, is this point clear, beta?
Yes, sir. Clear.
Okay. Yeah, Mansi, I will be sending the homework again, like as usual. Okay.
Okay, sir. Bye, sir. Thank you.
Okay, people. All the best then.
Bye, sir. Thank you, sir.
Okay, bye, people. Bye.